Welcome back to Advent of Code 2024, day 23. Got 3 days left. And 23 opens in a minute. Let's just wait for that. So, yesterday was the monkey problem, the monkey bananas problem. That was a pretty good one. It was good because it could have sort of relied on you understanding hash maps and how to use them properly, but it didn't actually need you to use any proper algorithms. Hello, DJ. 5, 4, 3, 2, 1. LAN party. Okay, nice short description. That's a worrying sign. As the historians wander around a secure area at Easter Bunny HQ, you come across posters for a LAN party. Scheduled for today. Maybe you can find it. You connect to a nearby data link port and download a map of the local network. The network map provides a list of every connection between two computers. Each line of text in the network map represents a single connection. So KH and TC. Connections aren't directional, so it's an undirected graph. Okay. LAN parties typically involve multiplayer games, so maybe you can locate it by finding groups of connected computers. Start looking for sets of 3 computers. So these are like cliques, where each computer in the set is connected to the other 2 computers. All right. This will be like a cubic time search if we just find all the sets of 3 interconnected computers. All right. I mean, this I could be done by now if I already had a library with a graph and a clique finding algorithm. So how many contain at least one computer? Find all the sets of 3 interconnected computers, so they could overlap. How many contain at least one computer with a name that starts with T? Okay. Okay, so all right, I know what we got to do here. So we want to create a graph. We had something before, didn't we? But I don't know which day it was. Doesn't matter, we can create it from scratch. So, graph, fine. It's gonna be undirected, so we want Alright, so self to edges equals default dict on a set. Define add edge b self dot edges u next to v and the other way around. All right. Okay, so we want to go. Just do this. Go through the input. UV equals line.strip dot split on, it's a hyphen character. So I want to create a graph. Graph equals graph dot add edge from U to V and V to U. All right, so we've got our graph, and then we want to find cliques. Now we could just can just do this. Just say for U in graph dot graph dot edges for V in graph dot edges. I mean, we could do it. Okay, let's do it like this. Nodes equals graph dot edges dot keys as a, I don't know how, just cast that to a list. Is it already a list? IU in graph dot edges. Let's say enumerate graph dot edges. No, nodes. For J, B in enumerate node. Hang on. If you enumerate nodes, but you start from start. Start equals I plus 1. I haven't used this parameter before. I should. This makes it cleaner. For K W in enumerate start equals J plus 1. Does this do what I think it does? So for now. Okay, so this should give us distinct nodes. If, let's say, V in graph dot edges really going to use the get neighbors function. Just do it like this. So V is connected to U, and V is connected to W, and U is connected to W. VU, VW, UW. We've got a what's it called? Clique of size 3, triangle. Huh. What was the thing we want? Find all the sets of the 3 interconnected computers. How many contain at least a computer with a name that starts with T? If any node dot starts with T, is it lowercase? For node in U, V, W, result plus, okay, just do this. Result plus equal that. Starts with this is cubic time. Is this actually what we wanted to do? Or wait, why did I not just okay, I could have eliminated a factor of n, I think. Well, reduce it quite heavily to the okay. If you range over edges instead of nodes. 9594. Nope. Alright. 9594. That. How many of these have we got? 3380. Also, it's really dark. How many contain at least one computer with a name that starts with T? All right. Just see what we're getting here. If V in graph to edges U. Alright, first let's change this. We want 4 V in graph dot edges U. So we want all of V's neighbors. This will be much faster. And we also want all of U's neighbors again. It's got to be a neighbor of U. They've both got to be neighbors of U. So V, we know that. That is true. That is true. So it's just if V in graph to edges W. So V is connected to W. Let's try that. 9594. Something's gone wrong here. Alright, let me look at the problem again. Start by looking for sets of 3 computers where each computer in the set is connected to the other 2 computers. Alright, let's try the example then. You don't need to enumerate here, just go for U in graph dot edges. Alright. Don't know what's happened. 42. It should be 12. Oh, of course. I am triple counting. No, not triple counting. Sextuple counting. Sextuple counting. Its result divided by 6. 7. Because I was counting again for every permutation of U, V, and W. You could I could probably do that more efficiently. Yeah, okay, anyway, it's 1599. Correct. There are still way too many results to go through them all. You'll have to find the land party another way and go there. Since it doesn't seem like any employees are around, you figure they must be all at the land party. If that's true, the land party will be the largest set of computers that are all connected to each other. That is, for each computer at the land party, that computer will have a connection to every other computer at the land party. In the above example, the largest set of computers that are all connected to each other is made up of Ko, De, Ka, and Ta. Each computer in this set has a connection to every other computer in this set. The LAN party posters say that the password to get into the LAN party is the name of every computer at the LAN party, sorted alphabetically, then joined together with commas. Alright, this is nice because this was basically the first proper program I ever wrote. And I wrote it horribly. I wrote it in Python though, but I wrote it horribly. It's like a really complicated backtracking algorithm where I had lists and I was removing things from the end and putting things back on. I didn't know programming, but we were forced to do it for our mathematics program. And I made it work in the end, and then later I rewrote it as a recursive thing. And it was much cleaner. But yeah, it was a clique finding algorithm for a graph. I didn't have a graph data structure, so everything was just a bunch of lists and... Oh, it was a mess. So, this is nice. We've come full circle. I'm back to my very first program. And that's crazy. Your very first program being a clique finding algorithm. It should be like, you know, like something really basic, like a temperature converter or something. That's what they made us do. The professors making us do it didn't know programming either. They were mathematicians. So they couldn't help. Alright, so, hello Yasha, thanks for the raid. Have you done this problem? If you have, that was pretty quick. Alright, so... Good luck with Advent, I've just finished. Oh, well done. I think... I mean, I could see it being quite quick, because it's a classic algorithm, isn't it? Well, clique finding, you can... Alright, how would you normally write it? Recursively. You could just say... the largest clique will be... I mean, we could either do this iteratively, we could just recursively add and remove, well, no, not recursively, iteratively add and remove in a backtracking way, or we can write it recursively. I think recursively would be cleaner. So we could say, define, oh, let me get my IDE open. Define max clique of graph edges. So we want to say Alright, so we're saying, what is the max clique of the first n nodes in this graph? And start will define how many nodes we're using. So we start with all nodes. So we're saying either node 1 is in the clique or it isn't. So clique with first node equals max clique of graph edges start so we want start equals, so what is this going to do? It's going to return a set. So clique with first node is going to be the clique of that, but we want to say first, let's make a list here. Okay, cliques. All right. Clique without first node. Hang on. Let me just reason this out again. So there's two cases where we want the clique with I think this is fine. So we first get that. hang on. So we want the base case. If start equals length graph edges -1. So if we've just if it's the singleton graph, we're going to return graph. Okay, first of all, let's get this out. Okay. Graph dot edges dot keys. All right, that's the nodes. All right. All right. So node. Let's call it node list. If start is length of node list -1, we just return the last element in a set. Okay, so that's the base case. Otherwise, we find the clique of the whole graph except for start, right? So it's going to be start equals start +1. And we decide whether or not we can add start into it. So we need to check if. So this is going to be a set. And then we want to say if all x in graph.edges. Yeah, so first node graph.edges start. All right, so here we can just say that. Okay, if all x in graph, so if all for x in, okay, let's call it sub. So if first node is connected to all of these, that means we've just made a bigger clique, right? So we clique.add first node. Otherwise, we just leave it as is. Return clique, is this right? That's recursive. I don't know, try it. Unhashable type set. Oops. First node should be graph.edges. Whoops. Nodes. Alright, so it says that's the biggest clique. Let's try it then. So clique equals max clique nodes, and then what do we do? Sorted alphabetically, then joined together with commas. Alright, so list of max. We don't need to cast a list. Comma. Alright. That 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nope. It is alphabetical. Is that even a clique? Alright, let's try this example then. There we go. So we stop printing things. Seven, and we've got TB, VC, WQ. It's not good enough. There's supposed to be a bigger one. No, there should be one. That's TB. That's size 3. We should find size 4. Kodekata. Alright, let's click node list. Starting from here. We're not really using this start variable, are we? Hang on. Is that... No, we sort of are, because we... Start equals... First thing I notice is the clique you return will always include the last node. Oh yeah, hang on. This is not correct, is it? Yeah, so... I got this step wrong. I'm trying to basically copy what I did before. Many years ago for my first ever program, but this step is not quite right. What am I trying to say? I'm trying to say, okay, so if we're trying to find the clique of the singleton set, that's correct. We just return that. Okay. Okay, so if we're trying to recurse, we're saying Ah, okay. No. There's two cliques we've got to find here. One with the first node and one without. No, this thing's wrong. So, okay. Without, clique, let's say clique without equals max clique, blah, blah, blah. Okay. Clique with... So that is strictly without the first node, and this clique with means we have to go to the edges of so it'd be the graph dot edges on so we take all the edges of start what are we doing? Nodes start. Find the clique amongst them. And combine it with node start. So, okay, so there's two possible cliques. One without, one with. We see which is bigger. Yeah, I don't know what I was thinking here. This is not necessarily the clique. This is just I'm forcing it to contain. Alright, so plus set does not define add. Whoops, it's that. Okay. Return if length width is bigger than else. Alright, is that right? Yeah. Maximum recursion depth exceeded. Bollocks. Tree cache. Don't know if that'll help. I mean, of course there's going to be a lot of recursion here from gotta make sure you don't reintroduce remove nodes into clique with. Oh, this is turning out messier than I remember. Clique with so it's got to be this. Oh, I see. So it's so it's going to be neighbor set equals, so it's going to be first take this so maybe we should just be passing a set. That's probably just the way I should do it. Yeah, okay, so let's just say forget about that parameter. That was okay, given a set of nodes, we say if length of nodes is 1, return this nodes 0. Okay, so if it's of size 1, we do that. Otherwise, we say just return nodes in that case, right? Well, yeah, that's true. I wanted to make a new object, but yeah, we're not modifying any of these objects, so it wouldn't matter. Temp nodes equals, let's just create a copy then. Copy nodes. Nodes.copy, I don't know. Nodes copy. Node equals temp nodes.pop. So pop an arbitrary node out. So clique without equals max clique of temp nodes. Find the clique of what's left. Clique with is going to be graph.edges on node intersect temp nodes. Is that right? So we find the max clique of all neighbors within that set and add start to it. Add the node. Is that gonna work? It's gonna be slow. Temp nodes is temp nodes set and list. Temp nodes is a list. So this should be a set. We didn't pass a pop from an empty set. What? Could this ever be empty? Yeah, it could be empty if there's no neighbors or whatever. Okay, fine. If length nodes equals 0, return an empty set, I suppose. To type. Also, that's a dictionary, isn't it? Kodekata. And that's correct for the example. Okay, that took me way longer than it should have. Would have helped if I just drew a diagram. Let's try this. Avax dagdi dodu page kiki ot q view. Is this bigger than before? Yeah. Correct. Okay. Uh, yeah. I mean, that's basically the same kind of recursion I used when I first wrote this program, but I wrote it a bit in a bit more of a messy way. Um, the reason I was doing that thing with start equals 0, like the index thing, is I thought it could be done in a more dynamic programming way, but it can't because this is actually an NP hard problem, clique finding. So you can't make it into like a quadratic time thing. Uh, yeah, it's exponential. Well, no, it's sensitive to the size of the clique, the biggest clique. So smaller the clique, the less time it'll take. But yeah, in the worst time, it is exponential. Like, what is this size here? One, two, three, four, five, six, 7, 8, 9, 10, 11, 12, 13. Yeah, if you wanted to find a clique of size 13, like the like the brute force way, then you would have to do n to the power of 13, which is insane. So you can just about find 3 cliques and 4 cliques. What is the proper term for them? So clique in graph theory. I don't know if they have names for like cliques of 3 and cliques of 4 and stuff, but anyway, they're called cliques. Induce subgraph G that is complete. So we're trying to find maximum cliques. It talks about NP complete at the top. Yeah. Yeah, so if the graph is not dense, it won't be nearly as hard to find them. And yeah, these problems are always not dense. As in a quadratic number of edges, it would be dense. But these are sparse graphs. And the opposite of a clique is an independent set. So you can find independent sets by finding cliques in the complement graph, where you invert every edge. Turan's theorem gives a lower bound on the size of a clique in dense graphs. Oh, I remember this stuff. Ramsey's theorem. It's interesting. So in our case, if yeah, but we don't have dense graphs, so I don't think there's any guarantee on the lower bound. Um, so algorithm to find max clique in graph. What's this? The max clique dine algorithm. Is this similar to what I did? Remove P arbitrarily. I don't think this is quite what I did. Uses coloring. I don't know. It's not quite what I'm... Geeks for geeks. I think they're doing a all right, anyway, we did it. So that was a very graph theoretic problem. I mean, it's not, you don't really need to know graph theory. You can just do a you could also just do a backtracking. You just start at a node and keep adding and removing vertices in order until you find the biggest you can. Do that for every node. Recursive is quicker to write. It always is, but recursion depth could be quite high. Not really. The recursion depth is going to be at most size of the nodes. How many nodes did we have? Well, this number of edges we had was 3,000. So let me see how many nodes we have. $520. Okay, so like Python fixes the recursion limit at 1,000. So we could be hitting the limit. You can just increase the limit using set recursion limit, but you shouldn't do that. And I did that once for an advent of code problem, and I crashed my computer. Like the stream crashed, the whole computer had to be reset. But I set it too high. You can set it higher to like 2,000 or 3,000 or so, and that should be fine. But you really shouldn't touch that. But when I was doing HackerRank problems, because they have like, you don't run the code locally, you have to upload the code and run it on their machines, then I would do it because it's their machines, I don't care. So I would always add set recursion limit to like 10 to the power of 8 or something. And that helped a lot. One person I raided into previously put set recursion limit to that. Okay, so that's like 9, 10. Yeah, you don't want it that high. I mean that could be alright if I mean I would normally do 10 to the power of 8 when I was using HackerRank's machines, and that seemed to be okay. It never crashed. But yeah, we rarely come across problems where the recursion would even go that far. In HackerRank, they used to all the time. All right, so check out the stats and stuff. Leaderboard. My leaderboard. Only one person solved it, truly not taken. Captain Coda's leaderboard. Only 2 people. I can see this being difficult for some people because it's a whole different realm. Graph theory realm, and it really helps to know graph theory. I mean, it helps a lot to recognize this as a clique. And if you've worked with cliques before, then you already have an idea what to do. Yeah, a clique is the lower bound. Is it going to be a lower bound on the number of colors you need to color the graph, where 2 adjacent colors can't be the same? Because if you find a clique of size n, then you must use n colors to color that. So that gives you a lower bound on the coloring number of a graph. It doesn't necessarily mean the graph can be colored with n colors, but it does give you a lower bound. You must use at least n colors. And coloring numbers as a whole. I mean, there's the 4-color theorem, which is one of the famous theorems, which says that a planar graph can always be colored with 4 colors. Theorem. You never need more than 4 colors, but this was notoriously difficult to prove. And it was proved using a computer, but it was verified. The code was verified, so it's a proof. But I believe they've audited the code and everything, so it's okay. So there used to be a proof of the 4-color theorem, which was written on 1 page, and it stood for 10 years as a proof until someone found it was false. And our professor gave us this proof in class and said, okay, your exercise until next week is to find the flaw in this proof. A proof that actually stood for 10 years. And we managed. And it wasn't that hard to find the flaw. So this just goes to show that sometimes if you think something's true, you sort of let your guard down. No one really doubted it, or at least people look through the proof and they're like, yeah, this looks correct. But the moment someone tells you, no, this is wrong, find what's wrong, then that actually gives you an extra motivation to actually find what's wrong. Like, I remember a bunch of us were sitting in the cafe looking at this, trying to find the proof, and we did actually find it. So it's not that hard to find the flaw, it's just you have to be told that there is a flaw, and that's the mindset you got to go in when you're reviewing proofs. You got to think, this is wrong, where is it wrong? It's so easy to just look at each line of the proof, say, yep, that follows, yep, that follows, and can we find the wrong proof? Is it this? Yeah, I cannot read that. Somewhere, you can probably find somewhere that's written down. You can try and find the flaw yourself, but it's an interesting. The 5-color theorem is much easier to prove, and it just needs some graph theory, number theory. Coloring on Klein bottles and stuff. Yeah, so that was cool. That was basically the first program I ever wrote, and it's like a horrible first program to ever write before getting into simpler programs, but I kind of had to rush learning programming just so I could do this stupid project, which was none of the professors knew how to do because they didn't program there, but they just gave it to us and they said, okay, this mathematics course now has a computational element. We don't know how to program, but we're giving you this problem. Just do it and hand it in and get it done. You can learn C for this, which I didn't. I learned Python because C was a nightmare. Can you imagine coding this clique finding algorithm in C? I'm sure some people are actually doing that for Advent of Code, but still. Most of my colleagues did it in C, and they had a terrible time. I told them Python was easier, and they're like, no, I just started learning C, I don't want to change now. Their loss. I think the year after our year, the university switched to MATLAB as the recommended language, and they gave everyone a CD with MATLAB on it and said you can use this. I still chose Python. MATLAB might be better than C, but it's still a bit weird. I wouldn't want to do it in MATLAB either for the graph algorithms. I mean, I would be more comfortable in C, to be honest, than MATLAB, but MATLAB at least lets you do some things with matrices. You can do matrix algorithms with graphs. I don't think any are relevant to the clique, but you can find all paths from A to B, all paths from A to B of length 2 by taking the adjacency matrix of the graph and squaring it, or raising it to the power of n to find all paths of length n. It's really interesting how that works. But yeah, there are interesting matrix methods for graphs. MATLAB still gets taught in university. I had to use it for a course maybe 5 years ago. Yeah, oh yeah, I'm sure it still gets used. I mean, it's a good piece of software. It's just not really. I wouldn't want to use it for graph algorithms, but it'd be more for like statistics and linear algebra stuff. Thing is, we had a choice of problem. Like we could choose. They had a graph theory problem. They had a statistics one. They had a linear algebra one. You had to choose like 3 or 4 of them. And I think I chose a graph theory one, a statistics one, a linear algebra one, and a number theory one. And there were a bunch of other ones, like, I don't know, like a fluid dynamics one, which I didn't do any fluid dynamics, but it did look like a nice problem regardless. Oh, there's a cryptography one as well. I think I did that one. All right. Is anyone still working on this? But yeah, nowadays Python has really gotten better to the point that I would never really choose MATLAB anymore, even if I needed something powerful. I would still choose NumPy and SciPy. It's like it's good enough for almost all purposes. Ooh, Scala. Tempo, Alex. I've rated Tempo before, so. Oh, this will be interesting. Oh, he's doing diagrams in Paint.
The largest connected components.
Or some form of Paint. All right, let's go check out Stew Squared. All right, thank you for watching, and see you tomorrow for the penultimate problem.